Okay, very good. Thanks a lot. Thanks for the invitation, and always happy to be here. So I'll talk about work in collaboration with Jonathan Luk and Igor Rodnianski on formation of trapped surfaces. These are the Einstein equations in vacuum. Right? But let me start with an introduction. So first of all, here is a, let me remind the PENROSE singularity theorem. So if you have a space-time which verifies certain properties, like the Ricci along null direction, so L is a null direction, is positive. There exists a non-compact Cauchy hypersurface on the space-time manifold, and there exists a closed trap surface S in M. So I'll define it in a moment what that means. That's the most important assumption. Then the space-time cannot be future null geodesically complete, right? So some kind of singularity occurs. You don't know quite what, but in any case, something wrong happens. So let me define the notion of a closed trap surface now. First of all, if you start up with a two surface, right? So we're interested in a two surface in M.
Is this the theorem of PENROSE difficult theorem?
No, it's trivial. Yeah, it's very simple. But I'll mention in a few words what it involves. Anyway, so you start up with a two surface, and you look at the null geodesics perpendicular to S. You have two of them in outgoing directions and incoming, and you choose L and L bar to be unit null vectors along these null geodesic generators, and you normalize them. But the normalization here is not so important. In any case, you define the null second fundamental form in the usual way. You take two vectors x and y which are perpendicular to S, and you take the derivative of L in the direction of x and y, the derivative of L bar in the direction of x and y, right? So these are the null second fundamental form. They are invariants relative to these null hypersurfaces which are generated from S. Okay, so now you can define the expansions as being the trace of this two null second fundamental form. Again, the trace relative to the metric induced, right? So this is the Riemannian metric induced on S. And the condition of being trapped is that both expansions are negative, right? So this is, of course, very different from what happens in Minkowski space. In Minkowski space, if you have a surface S, a two-dimensional surface S, then you have null cones, outgoing null cones, which are clearly expanding, and the ones which are incoming, which are obviously contracting. Here, both of them are supposed to be contracting. Okay, so obviously something very different from Minkowski space happens, and the result tells you that under these conditions you have you must have a singularity.
So can you just say what this definition of trapped surfaces again? I'm not quite getting it.
Okay, so once again, you have at every point on S you have two null vectors, yes, right, which are orthogonal to S. One which is outgoing in the direction of L, one incoming in the direction of L bar, right? At every point, you can define the null second fundamental form, right? It's a usual definition that you see in geometry, right? L is a normal. You define the derivatives of the normal in the direction of x and y, and similarly for L bar. And the condition is that the trace. So the trace the trace simply measures the expansions of volumes of these two surfaces. So if you move these two surfaces along this outgoing null hypersurface, the volume is expanding according to the value of this, right? So if trace chi is positive, it will expand. If trace chi is negative, it will.
So they're both shrinking.
And they are both shrinking uniformly at all points, right? This is very important. Uniformly at all points on S.
What happened to
Hawking? Forget about Hawking. I mean, this was the main thing.
I just remember this in their book.
Yeah, but this was the main result, and it's due to PENROSE. So Hawking had other results afterwards, but let me not get into that. Well, PENROSE was the originator of this theorem, and then Hawking had all sorts of other results which were similar. But the main idea was PENROSE. Anyway.
You refer to as the Penrose Hawking field?
Well, because Hawking. Yeah. Anyway, so here's a picture of how these null hypersurfaces will be if you have both trace chi and trace chi bar being strictly negative in all directions, right? So you see that the cones are clearly imposing. So you sort of expect something bad to happen. The proof, I'll just go very fast over the main ideas of the proof. So first of all, this is the main equation that's used. So really the only thing that it's used from the Einstein equations is this Raychaudhuri equation, which gives you differential equations for the expansion, so along these null geodesics, right? So the derivative of trace chi plus a half trace chi squared. So this is a Riccati minus chi hat squared. So you see you have something negative on the right-hand side, minus Ricci, which is also negative because of the condition. Chi hat is a traceless part of chi, right? So it's called the shear. So physicists call this the shear. Anyway, it's a traceless part of the null second fundamental form. Okay, so you obviously see from here that if trace chi starts by being negative, it will keep being negative, and it should explode in some sense. Should go to minus infinity. And then once you have this, you combine it with a little bit of topological nonsense, and you conclude that the spacetime has to be incomplete. This topological nonsense is simply just you establish a homomorphism from the boundary of the future of this surface S to the image on this hypersurface, which is supposed to be non-compact, and you get a contradiction.
But it's just incompleteness.
It's just incomplete. There's nothing else.
It doesn't say anything about the singularity.
It doesn't say anything about singularity. It's absolutely nothing, right? Okay, so here are the questions which are raised by the result. Well, first of all, as you just said, this is not a quantitative formation of singularity. So obviously you would like to have one. The Penrose argument doesn't provide any information on the location of nature of singularities. You have no idea. Second thing, which is more interesting, so these trap surfaces are very, very, as I said, very different from Minkowski space. And it's not clear that this sort of thing come naturally. You can put them in the data for the Einstein equations, but that's kind of cheating. So the question is, can they form in evolution in a natural way from data which is not trapped? So this obviously has to do with gravitational collapse. It should be an important step in the understanding gravitational collapse. And finally, the uniformity condition is really a very strong condition. And obviously, these are hyperbolic. Einstein equations are hyperbolic equations. There is lots of oscillation going on. There is no reason to expect such a strong uniformity condition being satisfied at some place. So the question is, what happens if you start up with non-isotropic initial configurations? In other words, configurations which are very far from being trapped. All right, so so let me talk a little bit about, so the result that I'm going to present first, I'll say a few words about an old result of Christodoulou, and then I'll present our new result. So the result of Christodoulou concerns initial data not on a space-like hypersurface, as it's usually presented, but on null hypersurfaces. So actually, what you have, yeah, actually, this is a good picture. So you have two null hypersurfaces. That's H, let me call it H0, and the other one is H bar 0. And you want to impose data here and construct a solution in the domain, in the future domain of dependence of the initial data. So the question is, how do you prescribe the initial data? I don't want to go too much in details. It turns out that you can first of all look at foliations along these two hypersurfaces. So this will be foliations by functions u bar along here and a function u. So there will be u bar and u. So u on h. So this will actually u will be in h bar 0 and u bar on h0. So this is some regular foliation, and you look at the surfaces which are generated, so the level surfaces of this. Imagine that they are compact for simplicity. They don't have to be compact, but let's say they are compact. And And then you prescribe the conformal class of a metric on these two surfaces in a smooth fashion. And that's basically how you set up the initial data. So it has all sorts of advantages. But in any case, for the moment, let me just simply say that given such a regular initial data, there is a result similar to the well-known result of Choquet-Blois for the initial value formulation on space-like hypersurfaces. It's a theorem of Randall, which says that for every given regular characteristic initial data, there exists a unique development in a neighborhood of the intersection, right? So this will be S00 here, right? So it's this surface here, the intersection between the two hypersurfaces. Okay, so you can complement this result with the fact that you can construct here, you can construct a double null foliation in the spacetime which you generate. So what is a double null foliation? Well, essentially, you extend these two functions. So you extend the two functions to functions which satisfy the Eikonal equation. So d beta of u is equal to 0, and the same thing for u bar. They're equal to 0, and they will be transversal to each other in the sense of this condition on the initial data. And then you construct the spacetime together with solutions of this Eikonal equation. So you construct u and u bar in this neighborhood of S00 that I talked about. So the spacetime will be foliated by this double null foliation. Okay, so and then I can talk in terms of these double null foliations. I can talk the maximal future development as being of initial data here. So in other words, I'm looking only towards the future. Of course, the result of Randall will also go to the past, but let's forget about it. We just concentrate on the future. And you construct the spacetime for u between u star and 0, and u bar between 0 and u bar star. Okay?
So what's the definition of u star, please?
So this will be how far you can go in the local existence result, right? So no. These are two functions. There are no other coordinates. I'm not talking about other coordinates. So this is just a general. So the maximum development expressed in terms of this double null foliation, right? So I'm looking at data which are prescribed here, and then construct a spacetime together with these two foliations. They will be also unique because you specify the data for u and u bar, and you get a unique spacetime together with a double null foliation. This is purely local, right? Let's not worry too much about it. I can always define a notion of maximality just like we do in ordinary differential equations.
Okay, differential equations again, but in geometry, it would be a function of the coordinates.
Well, it's not going to be a function. Well, you mean you are worried?
The thing I'm happy about is u star.
Right.
I'm not going to use u star, forget it.
Okay, so let's say that I'm looking at the double null foliation in which u and u star are defined, and I go to the maximum values of u and u bar for which this is defined. It's not important anyway. If that worries you, well, it's not important, right? But believe me, it can be defined. Okay, so once you have that, there is another remark is that I'm going to talk not so much about this class of conformal metrics, but rather than the shears. So you see, once you have the spacetime defined, I can talk about the double null foliation. Therefore, I can talk about this chi and chi bar. Okay? So chi bar will be defined for all values of u and u bar in this region, which I call d of u star u bar star. Okay. So again, this doesn't have to be maximal if you don't want. It's just a region. Yes.
What's the chi bar again?
Right. So given this normal, right, S, so you have chi. You define chi of xy is dxl y for the space-time metric, right? So now we have the metric, right? And then chi hat. So I can define trace chi And I can define chi hat as being chi minus a half the metric, so let's call it gamma. And so this is a metric induced on these two surfaces times trace chi. Right? So you take away the trace, in other words, relative to the two surfaces. Okay, very good. So this is a theorem of Randall. Okay, so now let's go to Christodoulou's result. So this is a 2008 result. So what he did was to specify characteristic data, just as I have it here, such that the future development du star. So you take this to be delta. So in other words, what will be u bar delta? U bar star will be in fact a value of a parameter delta larger than 0. Okay, so this is exactly where you prescribe the data here. And also on this other null, so you have two null hypersurfaces just like in that picture. On this hypersurface, he takes the data to be trivial. So actually, you can think about this side of the diagram, so this part of the diagram is being Minkowskian. So you are in Minkowski space, right? So this part is a data which is generated from the Minkowski space. And here you prescribe data. So this is where you have the freedom to prescribe. And you can prescribe this chi hat, this traceless part of the null second fundamental form here, essentially arbitrarily. Okay? So you have complete freedom of prescribing the data. Okay, so anyway, so he constructs a space-time. Now it's not local anymore. It has to be, in fact, semi-global. So it has to be, you have to define for sufficiently large value of the parameter going in this direction. So you go sufficiently far this way. And the result will tell you that if you choose the data correctly, you'll get a trap surface here. Okay? Even though you have absolutely no trap surfaces at this stage. Right? So you are perfectly regular at this stage, and you get a trap surface there. All right, so what are the initial data? Again, you prescribe, as I said, the traceless parts of the null second fundamental form along these two null hypersurfaces. You take this one to be 0, right? So this is trivial. And then you take chi hat 0 to be non-trivial, but still isotropic. In other words, it's large in all directions, right? When I say all directions, I mean all directions of two surfaces, right? Okay. So, and it's a short pulse in a way which we'll define precisely a little bit later. Okay. So, a short pulse relative to this parameter delta. Okay. And in all these results, you play with deltas, and you make delta sufficiently small in order to get the result you want, right? Okay. So the result which I want to present.
That's a dynamic formula.
So it's a dynamic formula, right? So this was the first result. So this was the first result, absolutely first result in the sense all the results before were in the spherical symmetric case and with matter. So this was without matter in the non-spherical symmetric case. Of course, you know, if you have matter, if you have spherical symmetry, you have to have matter, right? Otherwise you get trivial, right? Exactly. So, all right. So this is the picture again. Now, so what we did is that the result remains true for non-isotropic data. In other words, see, he had the result that he had was there is something large. So the data was prescribed here. So if you think about all two surfaces going this way, the data would have had to be large.
By the way, still in his work, there's still no understanding of
No. Of course, you just go up to the trap surface, right? Okay. So again, we took exactly the same kind of data. So it's trivial. So the space-time is trivial here. So the data, in other words, is trivial on this side, but it's non-trivial here. But instead of taking data which was isotropic, we take data which is actually concentrating along one null geodesic. Okay? So it's large. In fact, it can be, even here, it can be flat everywhere except along a null geodesic. And you still get a trap surface. So this was kind of a surprise for many people because there was always a sense that the trap surface is formed because of collapse of sort of a a sort of a uniform isotropic collapse of, I don't know, concentrations of matter, let's say. Okay, so.
And these are open conditions, right?
Yeah, these are open conditions. All of them are open. Yeah, in Christodoulou's result and also in our result. But I'll make it a little bit more precise. Okay, so this is, yeah, I should say, you see, if you look at, again, at this type of picture, Stefanos, thanks Stefanos for producing the picture for me. So if you look at this picture, you see this in Christodoulou's result, this will be the trap surface, right? So it's yeah. Right. Anyway, so you see in Christodoulou's result, the data is uniformly large in all this region, and the trap surface will be a trap surface of the double null foliation. So you construct the double null foliation, and the trap surface will be in fact belonging to that family. While here we construct a completely different one, and it requires a deformation argument. So you'll see.
By the way, do these things like quantitative in terms of where you, how long you have to wait?
Yeah. Everything is quantitative, right? Yeah, absolutely. I mean, less our result in some sense, because our result is slightly less quantitative because you don't quite know what this hypersurface, I mean, what this trap surface is. But you still know that it is in this double null foliation. Okay? So in other words, in the region constructed together with the double null foliation. You'll see, I'll say more in a second. Anyway, so here are just some normalizations which I make, right? So it's again the same kind of diagram. This is, as I said, this is a Minkowski space, so you can talk about R, the function R. A U bar is a usual U bar in Minkowski space. In other words, it's U bar in Minkowski space is just T plus absolute value of X. This you call R. U is T minus R, right? All the way up to here. And of course, here you take non-trivial data. And you arrange, so this is the axis, okay, right? So I'm writing everything in polar coordinates. This will be the axis. And here you have R equal to 1. So you fix the picture in this way, right? So you have R equal 1 here. You have this parameter delta as we had before. Okay, so again, you pick up flat data, as I said, so flat data here, and you take a short pulse of size delta on here. So let me now define what this pulse is. Okay, so this is Christodoulou's data. So remember that it's the shear, this traceless part of the null second fundamental form, which you prescribe, right? And you prescribe on this hypersurface. And the other one, of course, is, so the one along here is Minkowskian. So it's flat, so it's actually 0. Okay, so you choose it in such a way that whenever you differentiate, well, first of all, as you see, without any derivative of chi hat in an infinity, it has a delta to the power 1/2. And therefore, chi hat 0 blows up like delta to the minus 1/2 as delta goes to 0. So in other words, this chi hat 0 is large. Okay. So this is large relative to this delta. And if I take, whenever you take a derivative in the U bar direction, in other words, whenever you take a derivative in this direction, right, along the null geodesics, things go worse by a factor of k, which is natural because the length of this null geodesic is of size delta.
Delta is small.
So delta is small. Delta is a parameter which is at your.
But now why does that?
You have the half. It's just half.
Yeah, this is a normalization. So this is delta to the 1/2. It simply means that chi hat 0 behaves like delta to the minus 1/2, right?
Same in case, bigger.
So, I'm sorry?
Yeah, you need a lower bound, right?
Yeah, sure. But it could behave. You allow it to behave like delta to the minus 1/2. That's what I'm saying. You allow it to behave like delta to the minus. It can go all the way. To form a trap surface, you will need this, right? Okay. It will have to be proportional to delta to the minus 1/2. Right, but right now I'm looking at a set of data. I'm looking at a larger set of data, which includes those which will be trapped. Okay, right? So I'm looking at a set of data which we call C delta B. So it depends on a parameter B, which you have here, and depends on delta. These are angular derivatives along these two surfaces, right? So that we discussed. Anytime you take an angular derivative, things remain the same. There is no change, right? That's related to the fact that things are uniform, right? Okay. And of course, you take a certain number of derivatives. It doesn't quite, exact number of derivatives is not so important. Now, right, so Rodnianski and I later on, in 2010, we proved the same result. We simplified considerably his result, but we also allowed a larger class of initial data, which in particular allows you to concentrate on sectors, okay, on angles. So, so the idea being that it's very similar to this one. And it's unknown. Right. So you. So see, this is quite similar when you differentiate in the u bar direction. 4 and u bar are the same actually. So this is the same. But whenever you differentiate in angular directions, you allow things to get worse by delta to the minus a half. Okay. So you see. When you differentiate this way, you get a delta to the minus 1. If you differentiate along this direction, you get a delta to the minus a half, which means that you can concentrate in angles of size delta to the 1/2. Right? Okay. So it's
whereas before it had to be more.
You have to be uniform. Right. Exactly. So so this data is there is a relaxation of the data, which also leads to a much simpler proof. So it leads to a simpler proof because you instead of trying to prove this later on, right? The same kind of estimates later on, which is, of course, what you always have to do in analysis. You start up with a certain data, and then you want to show that the data, these bounds persist later on, at least for some time. Here, you prove less, but with much less effort, okay? And you also allow for a larger class of data. So that was the idea. Anyway, so. Trap surfaces. I don't say, for the moment, I don't say anything about trap surfaces, right? And right now, I'm just giving you a class of data, and then I'm going to prove certain statements about them. So, so the statement of 2008 of Christodoulou, it's better if I close it, right? Okay, so the statement of Christodoulou in 2008, and Rodnianski and myself in 2010, was that given a B, so given a constant B, so remember it was a delta and B, right? Given a constant B, and then u star strictly less than 1. This condition, u star strictly less than 1, is just tied to the fact that, remember, there was an axis here. So this was r equal to 0. And the maximum value will be 1, in fact. The maximum value of u would be 1 before you reach the axis. And of course, you don't want to reach the axis because you will have no control anymore. Okay? So, but it tells you that you can go arbitrarily far away relative to 1. And so anyway, so if you choose this constant, there exists a delta larger than 0, sufficiently small, such that if the data verifies this condition, okay, right? So again, the condition that we had before, or this condition, then the maximal future development, you don't like this. Anyway, some development, doesn't have to be maximal. You can construct the development up to u star delta, okay?
I don't mind what that is, as long as you make it trap, right?
Yeah, exactly. That's the only thing that counts. Right. Okay, so now, so you see, this is a purely existence result. It doesn't tell you anything about the trap surface, right? So I'm just telling you that given a certain data, I can construct a space-time for a sufficiently large value of u star, right? Okay, so now, the second part of the theorem tells you that if, in addition, if you look at this function, so this is a function defined on two surfaces. If you look at this function, so it depends on omega. Omega is an angle, right? If you look at the integral of this shear along a null geodesic, right? So it's along a null geodesic going this way up to delta, right? where the data is concentrated, then if the infinimum is larger than m star, then for any u star less than 1, there exists again a delta such that the surface is trapped. Okay? So the surface, again, being the last surface in this diamond that we talked about. Okay? So that's a result. Okay. Now, in our for our type of data, we also proved a companion result, which has to do with formation of scars. So formation of scars, a scar simply means that the surface that you obtain at the end will not necessarily be trapped everywhere, but it will be trapped in some region. Okay? So you can prescribe exactly the region where trace scar will become negative. Okay? So the expansion will become negative. Instead of becoming negative everywhere, it will become negative in an angle. And that's actually, this fact, it's much simpler to prove, in fact, than the rest. But it played a very important role in the result that I'm mentioning here.
Wait, that's not enough.
It's not a trap surface yet. Yeah, I'm just saying.
It's a building block.
Right, but I can control the double null foliation in such a way that I get something interesting happening.
It seems your work is localizing in
Right.
angles.
Right. It's much simpler. As I said, this is much simpler, but it was an important step in understanding this new result. Okay, so let me now describe the existence part of the result. Right? Now, in Christodoulou has 650 pages, 625 of which are the proof of the existence result. And at the end, he has the proof of the formation of trap surfaces. So after you read 350 pages, you find that there are, I don't know, 10 pages in which he proves the existence of a trap surface. It turns out that, of course, that's not the way to do it. I mean, in our paper, we put everything, we put this argument of formation of trap surfaces at the beginning. In other words, the second part, which is the formation of trap surfaces, uses this, but you can put it as a black box. You can assume that you have a black box, which is the hard part of the argument will be here. But once you have the black box, this part of the argument, which is the formation of trap surface, is actually very simple. It's very elementary. Okay? So the idea is that, first of all, you have the same equation as Penrose used, which is this Raychaudhuri equation. So this is an equation for trace chi. If you remember, there is a trace chi. I'm sorry? Yeah, he's only interested in producing a trap surface, right? So, the.
What I'm saying is he never used this, whatever you call this.
Of course, he uses it. Oh. Yeah, absolutely, absolutely. So the argument is based. So the argument is based on. So this is Christodoulou's argument. I'm presenting it in the second part. I'm presenting Christodoulou's argument, right? So Christodoulou's argument is if you remember, you have these null hypersurfaces. The null hypersurface going this way. So you have a double null foliation. You have null hypersurfaces going this way and hypersurfaces going this way. So this is the Raychaudhuri equation is in this direction. So you are looking at exactly the same thing as before. I put it as an error term. So remember, there was a 1/2 trace chi squared. It turns out that would be an error term. I'll explain in a second what an error term means, right? Okay, and then obviously this equation, if you just look at this equation, and if you are starting with something which is not already negative, there is no way you will be able to produce a trap surface, because even in Minkowski space, right? In Minkowski space, you have the same Raychaudhuri equation doesn't produce anything, right? The trace chi will go to 0, but it's in infinite time. So you are not producing a trap surface in Minkowski space. So obviously you need something else. First of all, you need to understand that this is an error term. But then you also need to take into account this, okay? And the way Christodoulou took that into account is by deriving an equation in these directions. So it's not in this direction anymore. You derive a similar equation in this direction. Now, all these are part of a much larger set of equations, which are called the double null structure equations. and which are a lot of them. So these are just two of a set of, I don't know, 20 or 30 equations. That, okay. Okay, so I can explain. So in fact, the first part of the argument has to use everything. Okay, all the equations, all the Einstein equations are used in here, right? You can't do anything without that, right? So let me explain. So first of all, you see, if I have a double null foliation, I can introduce a frame, a null frame associated with it. So in other words, I produce E3, E4, E1, E2. Okay, so E3 and E4 are the L and L bar, right? The null geodesic generators. And then E1, E2 will be tangent to the, I can choose it arbitrarily to be tangent to the two-sphere and orthonormal along the two-sphere. The choice of E1, E2 is not so important. I mean, you can be quite general in that sense. Okay, and then you define the connection coefficients, which let me call gamma, right? So what are the connection coefficients? You take all the covariant derivatives of the elements of the frame relative to the frame. You call that gamma, and then the structure equations give you derivative of d over du and d over du bar. So d over du bar. In other words, derivative along this or derivative along this, right? Of these coefficients in terms of curvature. Plus, there will be maybe some other derivative of gamma plus gamma times gamma. I mean, they are kind of complicated, but structurally, that's how they look. Okay?
So
right.
all the work is somehow to justify this error of delta?
Exactly. So all the work in Christodoulou is to justify the error terms. Exactly. Okay? Indeed. So these are not so difficult, but these are extremely difficult. So these are very complicated, in fact. And you cannot say anything about these error terms unless you have understood the whole argument here. Okay? So the justification of error comes up from here. Yes?
Not really the difficult part then?
Right. The construction of the space-time with given data, you know, the general result that I mentioned earlier. You give data and you want a set of data satisfying certain conditions. You want to show that you can construct a space-time for a sufficiently long time, right? Once you have that, you also have bounds. So this doesn't come up just as an existence result. It's not obviously it's not an abstract existence result. It's an existence result with lots of bounds. And those bounds will be used in order to justify these error terms. Okay? So that's how it goes. Oh, you need everything. Right. So okay. So you need. You will ask me how do you estimate the curvature? Well, okay. That's obviously the curvature. That's a key. The curvature you estimate by hyperbolic estimates. So you have to do energy estimates for curvature. So you have to combine energy estimates. You have to combine transport equations. There are also some elliptic estimates. There are plenty of elliptic estimates along two surfaces and so on and so on. So there is a whole analysis. To a large extent, sort of those kind of methods. So the methods which come here were the methods in the stability of Minkowski space to a large extent. I mean, using curvature, using energy bounds for the curvature, using transport equations for. Yeah, because he goes back through everything, right? Okay, so.
Where's the curvature here?
Yeah, for obviously, but he could have made it standard for everybody else, which he doesn't. Our proof is about 60 pages, right? So it's kind of a.
So where's the curvature come in? I mean, so that's just part of what you have to do to get the non-homogeneous.
Well, obviously, whenever you differentiate connection coefficients, you are going to get curvature on the right-hand side. Now, the curvature is really the main part, I mean, the main object, right? How do you estimate the curvature? Well, it turns out that the curvature satisfies hyperbolic equations. So that's where hyperbolicity of the equations come into play. You know, it's a long story.
You need that to get these control.
Everything. You cannot get, if you don't get both estimates for the curvature and estimates for gamma with many derivatives, you are not going to get anything. Okay? Right? And of course, you need the initial conditions. And you show, in fact, that the initial conditions, these bounds that we had initially propagate. Okay? That's the point. Then they propagate for a sufficiently long time. And therefore, because of the estimates you get, all these terms will be error. I mean, so this is a long story. I'm not going to go through all this because it's really a long story. I mean, this will take another hour.
If I can drop
Yes?
the error terms, then I'm finished. Is that more or less true?
Right. So once if you claim that these are not there, I'm done, right? So it's exactly what will happen in the next slide. Okay, so right. So now, not in the next slide, in the slide after. So here I'm just I'm just say that the result of Rodnianski, Luk, and myself require, instead of the infimum, requires the supremum. So if the supremum is sufficiently large, then you're okay. Of course, if the supremum is 0, obviously it's not true because you'd be in Minkowski space, right? So obviously, okay. So it's a it's very satisfying from this point of view because you go from infimum to sup, which is kind of a nice thing to do. All right. So anyway, so then if this is satisfied, then for every u star again, so u star is how far you go, with 1 minus u star sufficiently small, there exists a delta such that this domain contains a trapped surface. And again, the trapped surface is not one of the double null foliation. It's a completely different one. It uses all the ingredients in Christodoulou theorem, right? So in other words, part 1 and 2 that we had before, but with a new deformation argument along this null hypersurface. Okay.
But the Christodoulou condition, wasn't it forcing that the data is almost doesn't change too much on the sphere?
To some extent, yeah, of course. Of course. So that's why I say that it was an isotropic condition.
So if it didn't change at all on the sphere, there'd be no difference between sup and if it didn't change at all on the sphere.
Yeah, but you know, in our result, I can assume that things are 0 everywhere.
I think what he's saying,
yeah.
the way to say it is the conditions are not restricted in the side way. So it's very significant you're setting.
Right.
That the sup is not super.
Right. In other words, I can assume that everything is 0 except the longer null geodesic, right? Yeah. So chi hat 0 can be 0 everywhere except the longer null geodesic. Right?
That's the condition of Christodoulou to do something.
It had to be non-zero everywhere.
Much more non-zero.
It had to be non-zero everywhere.
I think we all
Right?
agree.
Right. Okay.
It's not argument.
Okay. So right. So the okay. So what's the new argument? Okay. So the idea is that you construct along u bar equal delta. So let me maybe make another picture here. So remember that we had this diamond, right? So this was of size delta, right? So this was Minkowskian here. This was H0. This is H delta, right? So this corresponds to u bar equal to delta, and this is u, and you want to go all the way to u star. Okay, so what I want to do, so this is a null hypersurface. I want to construct a trapped surface along this null hypersurface. Okay? So in this I'm going to do by a deformation argument. So deformation meaning I look for a surface. U bar is equal to delta because you are there, right? And R is a function of omega. So R, okay, so I have to tell you what R is. You see, if I have S of u and u bar, I can define an R simply by saying that 2 pi r squared is the area of SU u bar. Right? So this defines a function R which coincides with the usual R if you were in Minkowski space, right? Okay, so anyway, so I want to look at that function R as a function of omega. Okay, and I want to show that there exists such a thing such that it will be trapped. Okay, so I take R to be in C2. Okay, and in order to get what I want, of course, this function to be between 1 minus u star and 1 because it has to be in the domain of in which I have constructed my spacetime. And it has to satisfy an elliptic inequality. In other words, Laplacian minus Laplacian. So this is Laplacian on the 2 surface. Right? So everything actually happens here. You can reduce everything. So this, if you remember, this was S00. So it's the intersection of the 2 original null hypersurfaces. So everything happens here. I have to look for a function R is R of omega, which verifies this inequality. So if this is satisfied, then I have a trapped surface. In other words, this surface here would be trapped. Okay, so And then, of course, I have to show that such a functions exist if this condition is satisfied, right? Okay. In other words, if this M0 is different from 0. Right? So M0 has to be different from 0 at least at one point. That's enough in a neighborhood of a one point. Okay. So clearly, you see that if you were in Minkowski space, this would be 0, right? And it's clear from this inequality that it can never be satisfied because you can integrate it and see the integral, this would be 0, and you get that this will be positive. R is positive, so this will never be satisfied, right? So you can see why trap surfaces don't exist in Minkowski space. On the other hand, as we shall see, you can make, even in Minkowski space, you can make something which is quite close to that. All right, so now let's go through the proof a little bit more in detail. So the first proposition, and again, this goes back to Christodoulou. Under the assumptions of Christodoulou's existence theorem, you can show that this expansion along U and U bar, in other words, the expansion here along, I'm interested in what happens here. So I'm interested on a two surface, which is a two surface of intersection between the two null hypersurfaces, is equal to 2 over R of U0. So this is a radius, right? So this is something that happens here, right? So the integral takes place in this way, and I'm looking at trace chi along this null hypersurface, and the claim is that it's expressed in terms of the values of the function R along this hypersurface. Of course, remember that along that hypersurface, R is the R of Minkowski space, right? So this is just the R of Minkowski space. This is 1 over R squared, and this is M0 of omega, and these are O of delta are the low order terms, which depend on delta. So that's why you have to take delta sufficiently small. Right. So the proof. So the proof goes exactly. I mean, all you have to do is to integrate these two equations, right? So you first integrate this equation, and then you plug the chi-hat value. You plug it from this equation, integrating this equation. And the whole point is that these are terms. So this equation, again, as I said earlier, this will be very complicated, and you'll have no chance of saying anything. Okay, but it just so happens that they are terms. Okay, and then from this equation, it's very easy to see how you get a trap surface. You just have to make this strictly less than 0 everywhere uniformly, and you get that the infinimum has to be larger than 2 over 1 minus u star. Okay, so it's just immediate from the.
When you put error delta to size,
it's small relative to delta.
there's some fixed number of derivatives.
Yeah. I mean, so I'm simplifying a bit.
Just delta get 0
Right.
full list.
Right. Exactly. Yeah. Right. Okay. So now, so the second proposition, which is our new ingredient, is that you see what I want to do is to deform. Right, so I want to, it's an incoming, so I'm deforming along incoming null hypersurface. I'm starting here, and I want to get some hypersurface like this. Okay, and I want to calculate its trace, the expansion, because I want to show that the expansion becomes negative. And what I need to do is to relate this expansion of this deformed hypersurface relative to the expansions given by Christodoulou's result. In other words, I have to relate it to the trace of chi of the two surfaces generated by the double null foliation, right? So that's a calculation, and this is where you see this stuff, right? So the trace of chi prime, so the trace of the deformed surface is a trace of the old surface plus all this stuff, okay? Where R is that function that I talked about. And again, this is a standard Laplacian on A0. All right, so now if you combine this, right, so this is a new work in some sense to do this correctly. If you combine this with Christodoulou's result, we deduce that trace chi prime has to be equal to z. So I'm just simply putting the value of trace chi from Christodoulou's result, okay? From Christodoulou's calculation, I should say. And that's what you get. And now again, in order to see that this is trapped, you just have to make it negative. Okay? So to make it negative, well, this is the condition, exactly the conditions that you need. Okay? So you see immediately that all you need is to get an inequality of this type. All right, now, okay, so the final part is to show that, so this is step 3, is to show that such things exist, right? That you can find functions like this, which verify the two conditions. Okay, so first thing you do, you write R is e to the minus phi, so okay, you get an equation which looks down like this, right? You assume that, again, you assume that this is larger than m star, and you want to prove that there exists a function, okay, which will verify this inequality. So there exists a function verifying this.
So this is all on the surface.
So now I'm
Basically,
right, exactly. So I'm on the standard sphere. I'm on the standard sphere. By the way, all this can be generalized to situations where this is non-trivial. So then this is not going to be a trivial two-surface. But anyway, it doesn't.
This nonlinear equation, nonlinear inequality, an equation. This is very close to the equation of prescribing curvature.
Yeah, of course. Yeah, sure. Similar. The signs are different, however. Actually, the signs here are better.
You got a plus 1, which
The signs are better here, actually. I mean, so that result is, in fact, more complicated than this. This is very simple. Anyway, so you get, right, so you want to show the existence of functions like this, which verifies this relation, and such that you are within the domain, right? So you are also in this domain. Okay, so then you prove the existence of such a function. Phi is less than this. So epsilon now is the parameter.
it's a sphere. S2 is the round. S0 is the round.
Yeah, it's a.
So do you have to build in a conformal group? Often you have to.
No.
It's nothing.
That's what I'm saying. That it's simpler.
It's much simpler.
Yeah, it's much simpler. Yeah, the sign actually helps you rather than. Right. But indeed, it's very similar to the uniformization, right? What you get in the. Anyway, so. Here you make it a bit more quantitative. You assume that there is an epsilon such that this infimum is larger than m star on the ball BP of epsilon, right? So this is a small neighborhood of null geodesic. And you play with this parameter. So you construct the function phi depending on this parameter and the parameter and m star, such that phi is less than this log.
Let me just bring this up again. Is there, since you are doing geometry, is there no role to play by the because you could take a delta function, and you know that with an Onofre inequality, you move the delta function to be uniformly round. In other words, you've chosen coordinates here, but have we lost the chance of doing geometry on the sphere?
I think if you want to prove a stronger, if you want to prove, this is a simple. We decided, actually we had a lot more results, but we decided to put just this one because it's very striking. It's very simple. Everybody can visualize that things are happening because of what happens in a direction. But if you want something more, I agree. If you want to make it, even more quantitative,
if you have that freedom to move with the
you'll get
the sphere at this point, it would be very useful.
you expect to get stronger conditions. But in this stuff, we wanted to have the simplest possible thing because I think it's quite neat to see that you can take data which is 0 everywhere except in just anyway. So you take this epsilon, you construct this function. The functions are very simple to construct. So it's actually, as you see, it's almost a triviality. You solve you look for the fundamental solution of Laplacian plus a half on the sphere. So this is a delta function on the sphere at the point P. Since you are on the standard sphere, you can even write down exactly what that is. You then take a function supported chi epsilon, so a Kato function supported in this ball. You look for a phi tilde, which is like this. Then you remark most importantly, that this is less than 0. So in other words, everywhere outside the ball of radius epsilon, you satisfy already the inequality, because you can make it even less than 0. So by the way, this is something that you can do in Minkowski space, of course. So in fact, in Minkowski space, this was in fact, if you think about it, this was sort of the original intuition that if you are in Minkowski space, you can deform a surface to make it trapped in a very, very large set, except in the neighborhood of a point. But of course, in the neighborhood of that point, the expansion will have to blow up, right? So that's basically exactly what this function does, right? Okay, so all right. So now.
All this last part, I think, is probably going to flat nasty with the conformal.
Yeah, no, I agree, but yeah.
I mean, it's a group that's operating there and it does exactly this.
No, but we were aware. We were talking about this also, but in order to have a stronger condition. Right. Yeah, I mean, this at least, this is very easy to visualize. But in any case, you see, once I have that phi tilde, this is kind of cute. All you have to do after that, so phi tilde is good outside the ball of radius epsilon, but it's not so good inside the ball of radius epsilon. So to fix it inside the radius, you just add a constant, log of a kappa, which is small. Okay? So you take a constant which depends on these two parameters. So if I differentiate, this doesn't matter. So this inequality is still true. Okay? And on the other hand, on the ball where this is not true, I take the e to the infimum is larger than epsilon cubed divided by kappa c1, just because of these relations that we had here. Okay. Right. So and then then you can see that in order to check the inequality, the differential inequality, you have to show that this, is larger than this, obviously, which is larger than this. And now you want to make this to be larger than the supreme of Laplacian. But Laplacian is like C0 epsilon to the minus 2 in the ball of radius epsilon. And therefore, all you need is this condition, which gives you the kappa. And you are done. So that's all that is to it. And anyway, so conclusions. Large, highly concentrated disturbances can create future trap surfaces. And that I think, as I said before, was a bit of a surprise, because essentially all the conjecture that had to do with formation of trap surfaces, like the hoop conjecture, this is one of the famous conjectures in physics, have to do with uniform distributions of matter. Okay? Anyway, so though the underlying mechanism is relatively simple. And why do I say that? So again, the idea, the basic idea was a combination of two things. Well, first of all, in Minkowski space, you can deform a surface to make it trapped everywhere except in a set. And then once you have this other observation that Igor and I had with formation of scars. You didn't like that word, but it was very, you do the scar.
There's another theory of scars. You know that.
Oh. Then you are pushing exactly in the direction. You see, what you do is with those initial conditions, you fix up the initial condition exactly in the direction in which you are missing, and you create the additional push in order to have a trap surface. So that's very simple. But of course, to make it happen, you need all that stuff that comes up from understanding the dynamics of hyperbolic equations. So I'll stop here.